All right, so first up we have Drew Newman. Drew Newman got his PhD here not too long ago and is now on the staff at Carnegie. So he paid his way into getting to talk here. No, I'm just kidding. Thank you, Carnegie, for supporting this. Drew.
All right, so good morning. My task to kick this off is to summarize astrophysical constraints on dark matter, which is a huge topic, of course, that I'll just touch on, really. But what I thought would be useful, since we come from all different backgrounds and we have students, postdocs, faculty here, is to kind of provide a common vocabulary for our discussions the rest of the day and summarize from a galaxy observer's point of view what we know. So I just want to make a very few basic points at the beginning. As you know, we have a standard cosmological model. Dark matter is 26% of the energy density. And regardless of its particle nature, one can predict structure formation if the particle is cold, that is, it has negligible random motions, and if it interacts only gravitationally, so no collisions or decays. And those predictions have been tested in many ways. Famously, the cosmic microwave background that you see here, the temperature anisotropies in the young universe and their power spectrum. This is data from the Planck satellite. And the only thing simple point I want to make about this amazing data is that still the sort of vanilla lambda CDM cosmology is adequate to fit it. There's no extensions that are clearly demanded by it. And also that we now know the matter density, so we know the amount of dark matter mostly to 2%, which is pretty amazing. Now, if you take the density fluctuations you see in the CMB and allow them to evolve under gravitational collapse as the universe is expanded by a factor of 1,000, then you can predict the spectrum of matter density fluctuations, and that agrees with a range of observations covering scales of about 10 gigaparsecs down to about a megaparsec. So this is an old figure. There's much better data now, actually. But the only simple point I want to make is whatever dark matter is, it must behave a lot like the vanilla LCDM on scales bigger than about 1 megaparsec. Another important prediction that the vanilla LCDM model makes is not just the number of collapsed objects and their distribution and masses, but their internal structure. And so the run of the density with radius within a collapsed object, a dark matter halo, has a so-called universal form that looks like this and is characterized in the center by a cusp where the density goes like 1 over r. So this will become important later in the talk. So the topics that I want to try to cover here are what observations of the small scale distribution of dark matter can constrain its microphysical properties. So as we just saw on big scales, things kind of look okay, but as we will see, there are hints of deviations on smaller scales. And since all of the action, all these deviations are happening on subgalactic scales, that means that all of the physics of galaxy formation that we often just call baryonic physics often can mimic the signal that a non-standard dark matter picture would imprint. And so we have to work hard to disentangle those. But nonetheless, with current data, we can still ask what parameter spaces would be allowed for some non-standard dark matter. And as people in this room know much better than me, there are many, many different particle scenarios and so on envisioned. But usually, observational constraints are phrased in terms of a warm dark matter particle mass or a self-interaction cross-section. So that's really going to be the scope of what I talk about here. So for warm dark matter, the CDM power spectrum of density fluctuations is truncated at a free streaming mass, and lower mass things just can't form. And the things that do form collapse later and at lower densities. And it's usual that constraints on the warm dark matter particle mass are quoted in terms of a thermal relic. And the sort of scales of interest here are KeV masses. If you have some different production mechanism, then the same data will give you some different mass constraints. So that's important to keep in mind. Self-interacting dark matter has undergone kind of a renaissance in the last 5 years or so. And the idea here is to allow the dark matter particles to elastically scatter off one another. And for this, the cross-sections of interest for astronomy are sort of scales of sigma over m of 1 centimeter squared per gram, the usual units here, or about a barn per GeV. So this is like a really huge interaction for the particle physicist and basically the smallest value of interest for astronomers, order of magnitude. This could be velocity dependent and therefore scale dependent or not. And a nice thing about self-interacting dark matter is that, as you can see here, it looks on large scales just like vanilla CDM, and so you inherit all of the successes on large scales, but you start to see some differences in the inner parts of halos where scattering is occurring. That might explain some of the observations we're about to see. So I want to start on the largest scales, the biggest collapsed objects, clusters of galaxies. So this is an image, a very famous one, of two clusters of galaxies of order 10 to the 15 solar masses that are colliding at 4,000 kilometers per second. And so that gives you, as you might imagine, a lot of opportunity for dark matter collisions to occur. And this so-called bullet cluster actually still providing some of the best constraints we have on the collisional nature of dark matter. So you're seeing the X-ray emitting hot gas in red with a shock front. And as the clusters merged, the gas being very collisional has stalled in the middle, whereas the matter that you see in blue, traced by lensing, has passed through mostly. So by comparing the position of the gas and the dark matter, you can get an upper limit on the collisional nature of dark matter. On the other hand, the galaxies really act like collisionless particles. And so just as the gas lags the dark matter, if the dark matter lags the galaxies, that could be an indication of some collisions. That's not observed in the bullet cluster, but you get an upper limit. And actually, the strongest constraint comes from the fact that this thing didn't lose much of its mass as it blew through the bigger cluster. So the limits now are on the order of about 1 centimeter squared per gram. And there's some debate as to whether that maybe is a factor of 2, too optimistic or so, but something like that. There's a lot of work now going into finding more of these types of dissociative clusters, and especially measuring the positions of the galaxies and seeing if they differ from the dark matter. The difficulty is that you're centroiding a not too big discrete collection of galaxies, and there's just a huge uncertainty associated with that that is of the same order as what's expected for SIDM. And so far there have been about 7 of these clusters that were analyzed, and there's like a few hints that there's something's going on, but I would say overall the offsets that are seen are consistent with still collisionless dark matter. But work in this field continues. The density profiles in the centers of galaxy clusters can be very sensitive to dark matter collisions. These are measurable with many different techniques: dynamics, lensing, X-ray emission. And one remarkable thing is that over about 98% of the size of a cluster, that the density profile agrees really well with the canonical CDM shape. However, if you look at the very inner few tens of kiloparsecs, there is some evidence for a shallower density profile there that goes like r to the minus 0.5 or so instead of the canonical 1 over r. What does this mean? There are still observational uncertainties, I should say here, associated with separating the dark matter and the baryons. It's not trivial. But if you take it at face value, you could explain this with self-interactions with a cross-section on the order of 0.1 centimeter squared per gram. That lowers the density in the inner part of the cluster consistent with the observations. On the other hand, as is often the case, we also have explanations within collisionless CDM that are possible. Things like dynamical friction of the galaxies that fall into the center of the cluster, heating the dark matter. And so, but on the other hand, not all simulations produce those effects. So they're not obviously the answer either. And I would say right now we don't really know which of these possibilities leads to lower densities in the centers of clusters. Now I want to move way down in mass to what we'll call low-mass disk galaxies that have like 1 to 10% of the stellar mass of the Milky Way, but are much more dark matter dominated than Milky Way. And the usual technique here is to map a velocity field, in this case the H-alpha emitting gas, and extract the rotation velocity as a function of radius within the galaxy. And it was noticed pretty early on that in a lot of cases, these curves rise pretty slowly compared to the steep rise that's expected for a standard CDM cusp. And it's more consistent with a constant density of dark matter in the center. So this is usually called the core cusp problem. And this is a mature field now. There have been many gradually improving observations over time, retiring a lot of the uncertainties associated with them. And even though there are still uncertainties in things like whether the gas is on purely circular orbits and how to subtract the baryons, I would say the bottom line is that even when you look at the cleanest cases with the best data, you still see a distribution of dark matter density slopes that is shallower than you would naively expect for vanilla CDM. So typical log slopes of r to the minus 0.6 or so. In recent years, there have been a number of different simulator groups, like Ponson, Governado, and Brooks, that we're going to see, who have attempted to explain this coring of the dark matter in terms of supernovae in low-mass galaxies. So you're seeing a hydrodynamical simulation of galaxy formation, low-mass galaxies forming, and soon you'll see all these expanding red bubbles of gas that have been heated by supernovae. And this has important implications for galaxy formation, but also for the dark matter in the centers. Of course, the expanding gas doesn't couple directly to the dark matter, but it does so gravitationally. And in particular, if you have a really bursty star formation history, like you see in these simulations, then it can cause the gravitational potential to oscillate on short timescales that are not adiabatic, and this ends up transferring energy to the dark matter particles and expanding them and reducing the density in the centers of these low-mass galaxies, similar to what the rotation curves seem to show.
Over what kinds of timescales?
Less than the, as long as you do it less than the characteristic orbital timescale, I think it will be effective. But yeah, millions of years, I think. So that's not really a new idea, but what is new in the past few years is there are many different hydrosim groups who have produced converging results and showing that in the, sorry, some of the citations are being cut off here, but this is from a review by Bullock and Boylan-Kolchin recently. In the realm of the bright dwarfs, you expect an initial cusp to be flattened, and pretty consistent with this error bar that I've put to represent the data from a few slides ago. So that's very interesting and encouraging, and it also makes the prediction that if we could reach even lower mass galaxies, they should retain the cusps. It shouldn't be too affected by this supernova feedback because there's just not enough stars in them. There are also proposed solutions outside standard CDM for this. Warm dark matter doesn't seem to me particularly promising because you get lower densities because of later formation times, but you still have density cusps. Self-interacting dark matter, however, can create cores in the centers of the dark matter halos, and it has some other interesting effects. The coupling with the baryons in SIDM might be able to explain some of the rotation curves that do not appear to be consistent with being produced by this supernova feedback scenario. And I don't want to say too much more about that because I think we'll hear about it in the next talk by Hybo. Okay, now we're marching down to the lowest mass galaxies, so-called dwarf spheroidals orbiting the Milky Way and in the local group. These have stellar masses of like 1,000th down to 10 to the minus 8 or something of the Milky Way. And they're the most dark matter-dominated objects that are known, so they're really good labs for studying dark matter. And a fundamental prediction for cold dark matter is that a galaxy like the Milky Way, surrounded by lots of little subhalos here, all this substructure, that contrasts markedly to the 9 so-called classical satellites that were actually known around the galaxy prior to 2005 or so. So this is usually called the missing satellites problem, or you could call it the excessive substructure problem. And it either means that those just aren't there and our dark matter model is wrong, or that they contain very dim galaxies, or have just remained dark altogether. This is a very active field. So just in the last few years, the number of satellites of the Milky Way has doubled or so. This is due to panoramic imaging surveys like the Sloan and Dark Energy Survey. And the galaxies that are now being discovered are the so-called ultrafaints that go to luminosities about 10 to the 4 times smaller than those classical dwarfs that were known before. And extrapolating the current known systems, you expect on the order of 100 to 1,000 remain to be discovered. So indeed, it does seem that there are, in some of these subhalos, hosted extremely faint galaxies that just weren't seen before. And this is actually kind of a general phenomenon in galaxy formation. It's really hard to form stars in these tiny dark matter halos. And there are 2 main reasons for this. The first is that at reionization, all the UV radiation from galaxies heats the intergalactic gas and makes it unable to collect into small overdensities. And this drastically suppresses galaxy formation in low-mass halos below about 10 to the 10 today. The other important fact is that as soon as some gas comes into the galaxy and forms some stars, some of them explode and blow the gas back out again. So this regulates the efficiency of star formation to the few percent level and becomes increasingly effective at lower masses. So at higher masses, we've kind of mapped the stellar content of halos of various masses, as this shows. And if we would then kind of boldly extrapolate this into the realm of the Milky Way satellites, the dwarf spheroidals, that would allow us to predict what luminosities they might host, just based on their dark matter masses and simulations. And when you do this exercise, what you find is that the luminosities that are expected are in very good agreement with what's observed for the satellite populations of the Milky Way and M31. So it means that there aren't really like missing satellites at these luminosities. It's more just that only the most massive subhalos should be capable of hosting things that are as bright as the classically known satellites. So far, so good. However, a funny thing happens when you start looking at the densities of these objects, and that is that those most massive subhalos around the Milky Way have significantly higher characteristic velocities, higher densities than any of the actual known classical satellites. And this is really weird because although you can imagine, subhalos remaining dark, it would be weird for the most massive and dense ones to do so if lower mass halos are capable of forming galaxies. So this was coined the too big to fail problem, because presumably these most massive subhalos should be the most robust against feedback and unable to not form a galaxy. And yet we don't see their analogs. Another big development in the past few years, again, has been several different hydrodynamical simulation groups proposing solutions to this problem within standard CDM, due, again, mainly to supernova feedback in this case. So this is from the FIRE group. In the dark matter only case, you again see all of these subhalos that are too dense to match any of the known satellites. But when the full simulation with galaxy formation and baryon feedback is run, the densities of those subhalos gets reduced greatly and brought in line with the data. And in this simulation, it's mainly due to the effects of supernova feedback again. It's not evident that the problem is completely solved, though, I would say, because those same simulations that agree with the classical Milky Way satellite data, the black points here, when you would compare to similarly massive galaxies that are not orbiting the Milky Way but are found in the field, those retain H1 gas whose kinematics can be measured out to several kiloparsecs. And they're clearly not in agreement with those simulations. And this is potentially a harder question to solve because feedback should mostly be effective where the stars are forming and not really able to redistribute dark matter on much larger scales. So I think this is an open question. There are also, of course, dark matter-based solutions to the low densities of the satellites. For warm dark matter, most people find you need a mass of 1 or 2 keV for a thermal particle. And that's really too light to be consistent with other constraints from like the Lya Forest and the number of satellites that we observed around the galaxy. And so that's not a very promising solution, but there could be more room if you have like a mixed warm and cold scenario or something like that. For self-interacting dark matter, there's a huge range of cross-sections that would be capable of reducing the densities to the levels that we observe. So that remains an interesting solution as well. So far we've just talked about kind of the densities of these very low-mass galaxies, and not the density profiles like we measured in the low-mass disks and the clusters. And the reason for that is that we don't have like a disk with matter on simple circular orbits, which is kind of easy to interpret. You have a ball of stars, and you only have the radial velocities for like maybe a couple thousand stars at most. And that kind of data constrains the mass at one radius pretty well, but the slope of the density profile is degenerate with the orbit distribution. And so it's very hard to measure this right now at present, but there are some cases where there are multiple chemically distinguishable subpopulations within a galaxy, each of which constrains the enclosed mass at some different radius. So you can, 2 masses and 2 radii give you a slope. And for Fornax and Sculptor, at least, the results show a shallow density profile, again, like we saw in the low-mass disk galaxies. So that's very interesting. And this, I think, is an area that's going to be very exciting over the next decade or so. 30-meter class telescopes will really be able to measure many more radial velocities, but also critically measure the motions of stars in the plane of the sky, the proper motions. And so then you have the full 3D velocity vectors, and you can break some of these degeneracies. And so whereas now we have this huge degeneracy between the dark matter slope and the orbits, with proper motions, we expect to get down to about an error of 0.2 on the logarithmic density slope, and that will just be a huge change. And if we can get to things below about 10 to the 6 solar masses of stars, those are predicted to not really be affected by supernova feedback so much, and so they ought to retain a cusp if they had one in the first place. In the last few minutes, I just want to talk about a few constraints beyond the local volume on low mass structures. So high redshift galaxies actually provide some really interesting constraints on warm dark matter models. This is just because small halos can't form, and the ones that do form are delayed. And so the way to read this plot is at each epoch, you have some volume density of galaxies that's observed, and there should be at least that many dark matter halos. And so that gives you a lower limit on a warm dark matter thermal particle mass to have that many halos. And from the deepest pointings of the Hubble telescope now, those limits are about 1.3 keV. There's a single really faint lens galaxy found in a tiny volume at redshift 6 that gives you a limit of 2.4 keV, which is pretty competitive and interesting. This will become undoubtedly tighter constraints over the next few years after the launch of the James Webb telescope next year. Currently, the best claimed constraints on warm dark matter come from the Lyman alpha forest. So this is in the spectrum of a background quasar. You see imprinted Lyman alpha absorption of all the intervening H1 gas, and the statistics of these fluctuations can then be related to the underlying matter power spectrum. And currently, the best analyses have lower limits of 3 to 5 keV. And that's really interesting. This one is like free streaming masses of 2 × 10⁸ or so. And it would basically say that free streaming is just not a relevant phenomenon to explain any of the discrepancies that we've been discussing in this talk. There are some uncertainties associated with it still, like thermal broadening can sort of mimic the effects of warm dark matter, so you need to know the equation of state of the gas and how galaxy formation has influenced that, and so on. And so there's some debate as to how robust this is. I'm not really an expert. These could be slightly overstated limits, but they're still, I think, very impressive. We'll have an entire talk later today by Simon, but I just wanted to mention that a key prediction of cold dark matter is all of this substructure, and we've seen that many of these tiny subhalos might be completely devoid of stars, and so we need some other ways of finding them if they exist. And maybe the most promising method is strong lensing, where you have multiply imaged source here. And if you essentially measure the positions and fluxes of those images accurately, they turn out to be very sensitive in the zone of these images to low mass things like this 2 × 10⁸ mass substructure that was found. And so this makes it possible at cosmological distances to actually detect low mass things even if they're not luminous. And so I don't want to say too more about this field. It's very exciting because Simon's going to tell us all about it later today. So just to kind of conclude, like roughly what is the current state of things right now from my perspective at least. We have this huge range of observations over a big range of scales, from dwarf galaxies up to clusters, and in their own way, many of them are suggestive of some dark matter physics beyond vanilla CDM. And it's even possible to combine these different constraints and bring them to bear on specific particle models. So Manoj may talk later today about this work, where parameters of a dark photon model are actually, you have closed contours here when you bring to bear all of these galaxy to cluster scale constraints in this mediator mass versus particle mass plot. And that's just amazing to me that we can do that kind of thing. But on the other hand, it's also important to keep in mind that in each individual case, we have still plausible explanations within vanilla CDM that arise from galaxy formations and so-called baryonic effects. And so a single one of those isn't going to explain everything, but several of them working in concert still might. There is, though, reason to think that in the next decade or so, we'll have observations that are more definitive. I'm just highlighting a few exciting directions, I think, for the next 10 years or so from an observer's perspective. For these low-mass disk galaxies, as I mentioned, there are multiple different simulator groups now that are robustly producing cores. And they can now go beyond that and predict other correlations that you might expect to see. So we can test whether this supernova-driven core formation, which is plausibly happening, is what is actually happening in these galaxies. For the 30-meter class telescopes, we should be able to measure the density profiles of dwarf spheroidals. And that will really be a huge advance if we can get down to masses that should be insensitive to supernovae effects. And finally, strong lensing provides a very promising way to detect and characterize the dark low-mass substructure that must be present if dark matter is really cold. And that'll be the subject, again, of Simon's talk later in the day. So that's where we stand from sort of my observer's perspective. And Thanks for coming. I look forward to the rest of this interesting workshop.